Hi. This video we're going to go over Chapter 2 as well as a very brief introduction to the ultra basics of Matlab. Just going over some of the real basic functionality, how to load files, how to load variables, how to clear some of those operations, as well as going over Chapter 2 in the textbook, which covers the ultra basics of mathematics and a refresher to things like ODEs, Taylor series, and other topics in mathematics that are very essential for understanding the rest of numerics in the course. So let's go ahead and just go straight to Matlab. This is the very generic window that you're greeted with whenever you open things up. Most all of the outputs and then some of your inputs, if you're operating directly command by command, come in the command window. This is very much like a console command window you might see in a typical computer, CMD, that type of console interface. Except this is specifically just for Matlab, doing mathematic calculations. Matlab is very well suited for matrix operations. In fact, most of the notation and input and variable descriptions assume that the variables are saved as large matrices. Many of the algorithms are optimized to make the most use of that type of data arrangement. So one thing I wanted to start loading up as an example is a code that we actually use in Aerospace Capstone. This is some of our very involved optimization code, and this will show you what some of the different windows can do. Initially, I'll just load some files. We have 1, 2, 3, 4, 5. That one's useful. 6, 7. You got about 9 or 10 different M files. We have all these different extensions. TXT for text. What is Word? WRD. XLS is Excel files. XLSM is an Excel file with a macro. .m files are Matlab files, and typically they are just text documents. They're not encrypted. They're not encoded. They're not protected. It's just a fancy text file. These set of files all work together. Each one defines a function. We'll be going over that in detail. You'll learn how to write functions, both your own and use functions that are inherent to Matlab. There's a very large library that makes your life very easy. This is a multi-input, multi-output function, but I am getting way ahead of myself. The intent is just to show you that a lot of pre-canned code can be written by individuals, shared on the internet. There's an entire Matlab repository of information online, and you can post your files that work, and you can download other people's files that supposedly work and bug fix them for hours. So that being said, you can do very basic stuff in the command window. This can be a very expensive calculator. 1 plus 3 is 4. Whatever. 2 times 7. It does math. Saving as answer, you can do answer divided by 2, calling things back to the same way you would in a calculator. You can assign variables. And in fact, let's do that right now to show you the next window. A equals 8. Congratulations, you've assigned that variable to the number, or you've assigned 8 to the variable A. So now over on the right in the workspace window, where it is by default, you now see that every variable, both the answer variable and the A variable, are displayed. If you make 20,000 different variables automatically with a script, guess what? You get 20,000 different entries you get to scroll through. Congratulations, you don't know what anything is. If you have a complex variable, you're able to double click it. In this case, it is a 1-by-1 double precision variable. It stores one value, 8. But you notice this looks like an Excel sheet because, well, it's a giant matrix, or it can be a giant matrix. If you wanted to save a larger variable, in fact, I'll just write this initially. We'll go over matrix notation here in a bit. This will show you now that I've redefined A as 3344, and that variable shows up here in the display. Notice that the editor and the variable viewing window occupy the same space, so you have to kind of flip back and forth, and you get subtabs. The windows can get rather complex, so just manage them. It'll be fine. The working folder is actually kind of an important deal that gets a lot of new users hung up. Like for right now, if I want to use this function, I can press auto execute F5. It shows me an error message. It says it can't find the wait.m file in my E drive, blah, 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 DBF, Matlab optimization. It can't find it in the current folder or on the default Matlab path. It's very common. If you have a script saved in some folder, you typically separate folders with projects, and that makes sense. You can either add it to the root Matlab directory path, which, if it's going to be a temporary project only lasting a month or a semester, maybe that's not the best way to go, because then if you have different functions doing different things all called function 1 in 7 different project folders, well, which file did you actually just call? It's much easier to keep them separate. So just click change folder, and now you see that Matlab is actually pointed over here in the current folder window to the entire path going through fall 2017, 4273 capstone, DBF, MATLAB optimization, and then inside of that folder structure we have all these different codes. In fact, those are some airfoil data files. And one thing I have not yet got to, but it's important to know the working folder. You can set it manually, you can open up folders, you can go up one level back, you can open up a folder directly, however you want to go about it. Make sure you're working in the place you think you are. If you're saving data through the file system, if you're writing scripts that we're going to read data or output data, make sure that you're reading from the right place on the hard drive. Of course, you guys will get so advanced so quick, you'll be manipulating these through scripts without any problem at all. The other thing I said I was going to show you in a minute is I'm going to drag in a file called testing vars. You can see it listed right there in the folder path. I'm just going to drop that into MATLAB, and you notice that this immediately populates a whole set of data. This happens to be the variable set that our optimization code, this complex setup, requires to run. So you see we have several different airfoils. In fact, if I pop up on one of those variables just to take a look at what's inside of it, this is actually airfoil data. So CL, CD, CM, and I forget what the last variable was, but we really only use CL and CD for. That is the, actually some student made that one, 22222. The 2412 would be a much more common NACA airfoil designation, and this is a set of its polar data. So all of this can be referenced in scripts, so just keep in mind that variables certainly do not at all have to be single numbers. In fact, MATLAB's nice enough, it gives you the size of those variables. Helps you avoid conflicts in your programming. Alright, so that's the basic tour. The one other thing worth looking at, especially as we just finished talking about notation and scientific notation, manipulation of floating point variables in some of our initial lectures, is how MATLAB shows these numbers. So let's read out... this should work. Battery variable 2. Yeah, that's fine. So it's a fancy way of listing that this has a voltage of 1.2 volts per cell. But it adds all these extra names and numbers, and it might be preferable to not have that scientific notation if you just want quick, easy to read output. So if you go back to the Home tab and click Preferences, the place you change this is under the Command Window Options, Text Display. So by default, I believe it's Short Engineering and Loose Display. Actually, I think it's just Short and Loose. So if we click Apply and we rerun, actually another handy thing is press arrow key up. You can go back to all your previous commands. There they are. So we run battery 2. That should be the default format of MATLAB. If you change preferences, you can go up here and choose all the different display methods. One of the most intuitive is Short G and Compact. That way you can actually list a number as you might write it by hand on a piece of paper. Not great for lots of sig figs, very long numbers and digits, but hopefully your output is something a bit more concise to make it useful. My preferences, you have your choice. That's why they call it preferences. Short engineering, long engineering display. This is, again, just display. This is not how it is performing the underlying mathematics. The mathematics in MATLAB are performed with very high accuracy calculations in the intermediate for the same reasons we've just taught you in the first day's lectures. So anyway, that's where you can go to change those display preferences. I think a lot of people have their own preferences. Two commands that are very, very useful. One is CLC, clear the command window. The other thing can be very useful, clear vars. This is very handy if you have a bunch of variables and you don't want to simultaneously click delete, 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 delete all over it on the right. You type clear vars, press enter, it's gone. Just really helps you keep the screen tidy and everything. And of course you close all these files with the command, you click that and it's gone. That is the ultra basic introduction to what MATLAB can do. And we're going to be using this as we step through Chapter 2 to go through some very, very basic mathematic fundamentals. To give you a useful discussion of mathematical basics as a refresher before we get into some of the more complex or new theories to you in this class, I'll be following the topics of Chapter 2 in our textbook more or less in order. So it starts ultra basic. Definition of a function. If you have some description function of perhaps one variable x, most common, the biggest thing to remember is that you cannot have a function that defines two values for one value on the x-axis. So this line I just drew cannot be represented functionally. You cannot define a single function to define a circle. You say, well, that seems weird. We have these algebraic functions that my teacher told me was the formula for a circle, but if you look at it carefully, they have two solutions. There's always going to be a plus or minus somewhere in there. A continuous nice function would have one value, one particular value at every independent variable location. In this case, x is the independent, y is the dependent variable. In fact, instead of y, I could write actually, this would be the output f of x. It would just be the output value. So this is a one-dimensional function. Two-dimensional functions produce surfaces. Three-dimensional functions produce fields. And the dimensions mean how many variables you're feeding it. So f of x is 1, f of x and y is 2 dimensions, f of x, y, z, comma, comma, close. That's a three-dimensional function. You're feeding it 3 different variable inputs, getting different outputs. Okay, that was fun. Limits of a function. All right, let's say that you have a particular value here. Say that value is 4. On the right-hand side, since it's sloped up, you might have a value of 4.2 and 3.8. Limits, hopefully we've all crunched plenty of those, but mathematically, it basically says that as the distance decreases between the spacing of 2 calculated points, the limit approaches the actual value at some interested point. We'll call that point A. So the limit of a function as the function approaches A is not looking at the actual value at A, because sometimes that value can't be calculated. Especially for functions that approach singularities or some other sort of problem, it can be handy to know the behavior of the limit as you approach it, but not while also not being able to calculate the actual function itself. So the limit as a function approaches a particular point. It can be very useful in numerics and useful for physical systems. The idea of continuity. We've started with a well-behaved continuous little squiggle, and that is a nicely continuous function. Let's see if I can just clean this up ever so gingerly. There we go. This would be a continuous function, which also has the definition of being everywhere differentiable. So continuous means that it does not have any breaks. A discontinuous function, if I can delete that for the moment and erase my little canvas here, discontinuous function might be something like that. And of course, you'd have to define either a closed end or an open end accordingly, because you can't really again, if you said both ends are closed at this same vertical location, that's no longer functional. Because that particular value of x, you have 2 values. It doesn't work. So the idea of open and closed end functional representation is important. That would be a discontinuous function, though, which actually would have 2 different limits whether you're approaching from the right or the left. We will really probably not discuss, except in special circumstances, the behavior of these function and numerical methods. They create problems for most numerical methods because of that giant change in the derivative and functional value right as you hit that location. So we will stick, especially the first part of this class, with nice, well-behaved, continuous functions. Now I also said that this is just gauging by the beauty of this squiggle, infinitely differentiable. That means everywhere on the function you can calculate a derivative. Previously with that jump, the step function, I mean, what is the derivative? Right as you go across that boundary, is it infinity? Is it, you just say it's 0? Do you say it's undefined? With a function that has a value everywhere, and with a function whose derivative has a value everywhere, it's infinitely differentiable. Tough word to say, whatever. Intermediate value theorem. This is a topic your book covers, and it's ultra common sense. If you have point A and if you have point B, the intermediate value theorem says if you have a continuous function that is everywhere continuous between those 2 points, you don't have any jumps, well, a point exists between A and B that has the value between A and B. So if A was 1 and B was 3, somewhere between those 2, the function passes through 2. Okay, derivatives. Derivatives have a very explicit mathematical function that you're looking at, fundamentally the slope. The slope at a particular location, A, of a function. And derivatives are annotated by f prime or f double prime for the second derivative, f triple prime for the third. You just keep stacking these primes as you go down. You can also see f dot. It's usually for a time-based derivative. If you're taking the derivative with respect to time, Those are called temporal derivatives. If you're taking the derivative with respect to space, it's obviously a spatial derivative. In this case, space is not like stars and empty stuff up in the sky. Space is distance, one-dimensional space, two-dimensional space, three-dimensional space, where we live. Yeah. Anyway, the explicit mathematical definition is the limit as x goes to a. So a is the location you're taking the derivative about. Of course, the derivative will be different, or I should say can be different at different points of the function. Doesn't necessarily have to be. You've hopefully seen this in a pre-calculus class, high school course. We're not really at rocket science levels yet, but this is very fundamental. So it's basically looking at the functional change across an explicit distance and then taking the limit as that distance goes to 0. So numerically, we're going to keep this distance larger than the mathematicians would probably love for us to. You might say, oh, if you're just looking at the change in altitude of a hill across 1 foot of change in any direction, that's a pretty good estimate of the derivative. You're probably right if you're looking on a continental scale. But perhaps if you changed your resolution down to 6 inches, you would get a little bit different slope. If we change that resolution down to 1 inch, maybe now you start to calculate the limit, the slope and the inclination of the anthill you otherwise skipped over the first time. So by changing the resolution, and in this case resolution is given by the distance, let's use a different color, x minus a, that's essentially the resolution of your limit as you're taking the derivative of a function. As that decreases, you, for a continuous function at least, obtain a better estimate of the derivative. Now this goes right back to our representation of very small numbers in machine code and the bit depth we choose to use to represent numbers. If x minus a, if I can consult the book back here a little bit, starts to approach 2.2 times 10 to the negative 308th numerically, that's a problem. Our computer cannot differentiate smaller numbers than that. So at some point you've used too small of a step, you've used too tiny of an increment. You start actually getting into numeric problems and round-off error, truncation errors, all the different kinds of total error sources that can come up. So there is a problem at some point with numerically taking a derivative across too small of a step. Much more to come about that. You'll probably hear these topics arise several times in the class. But moving on forward, derivatives are of course the slope. I need to reiterate that as well. You can take first derivatives, second derivatives, and you can of course combine them in what's called the chain rule of differentiation. So if you have the need to determine dy over dx, and you were given on an exam by some mischievous professor, dy over dz and then dz over dx. Well, chain rule is so complicated you just look like, okay, we'll multiply this together. That's what they were in anyway. This is actually dy dz over dz dx. Hey, look, they cancel out, giving us the actual derivative we were looking at in the first place. It took me much longer in my life than I'd like to admit to realize it was actually that simple to understand how the chain rule worked. The mean value for derivatives. This one is much easier to understand graphically than reading the actual explicit formulation. Because what it really says is that if you have, let's say you run a function 2 times, some mysterious unknown function, and you again get these wonderful points a and b. I think they're going to be our favorite little happy trees of this semester. If you get 2 points a and b between each other, you could suppose that the derivative between points a and b is linear. You have no good reason to other than that's just the easiest way to estimate a derivative. But the mean value theorem says you're probably right at least once in that gap. It says you will be right at least once in that gap. Let's say you all of a sudden figured out how to plot your original function algebraically. Let's say your function looked like that. Continuous, though massively different changes in slope. But in this occasion, there are 2 spots where the derivative actually matches that mean value. So the mean value theorem says that regardless of what the function is going between points a and b, there will be at least one point that matches that derivative. So the 2 points that would match on slope would be a point there-ish and a point there-ish, of course, to the limits of my poor drawing skills. You can see at those locations, the function has a similar slope, a similar derivative. So we can see that's become true in this case. Let's look at a little bit less complicated example, perhaps at one that only has one location where it lines up properly. So let's say that was our actual function. Guess what? It's still correct because at this location now you have a derivative that lines up more or less exactly. So the mean value theorem gives some credence to us being allowed numerically to expand this gap between derivative points, between functional points. Because think about it. If A and B are a solution to a simple polynomial equation, your computer can calculate millions of those per second. Not a big deal. You just brute force the thing, find the answer you want. No need for higher order tools. The point of numerical methods and the point of minimizing the number of functional calls you have to have, because keep in mind, A is the answer to some functional value at x1 might equal A, and then function called at location x2 equals B. If this function was a CFD code run that took $100,000 of computer time on a web-based, cloud-based cluster, you're going to care a lot about how many of those functional runs you have to calculate. You want the most efficient numerical algorithm that's going to converge this solution as fast as possible so you save $100,000 of computation time per functional definition. Think of that as the example and the need for minimizing the number of functional calls. It's not for these academic and educational problems that we can just even have our TI calculators smash out answers faster than we can even release the answer button. So that's the real point. It shows us that there is a mean value between the two locations that holds and that matches the intermediate derivative, and expanding that distance between points A and B to have some knowledge that the derivative at least passes through that is a very valuable outcome. All right, definite and indefinite integrals. So definite integrals are when you have functional evaluations from two values, basically saying from A to B location. So if I can again clean up my nice little drawing here, undo the mess I have made. So much better than whiteboard, really, don't you think? Okay. I think actually in the classroom I'll be teaching it. They have chalk. It's very quaint. All right. So in this functional value, if you had a definite integral, you might say from A and B, even though this function continues elsewhere. I mean, it just keeps going. But you would be integrating from these two parts. That is a definite integral. An indefinite integral is where you're concerned more with the algebraic output of what the integration of that function becomes when it's taken to a higher order. So a indefinite integral would be like the integration of 2x squared. Of course, that becomes, gosh, this would be embarrassing if I messed it up here. X cubed, it would be 2/3. Just take the derivative, 3 cancels out. Yeah, you get that. That should be it. So that would be an indefinite integral example. An example of definite integration is where you either have limits here, maybe you go from A to B, or you have some graphical methodology where you go from A to B, start splitting this up. This is probably how your high school or elementary or whatever teacher taught you how to integrate. The first time they said, oh, well, you just stack up all these different columns. You sum up the area beneath, and that is the integral. And it's true. I mean, that is what integration is. This is, in fact, your book calls out as being a Riemann sum, where you actually take the functional value at each one of these locations. You consider it a rectangle. It's a crude method of taking an integral compared to some of the things you'll learn this semester. But, hey, it works. It's easy. And if you make those little gaps small enough, the answer is indistinguishable from some really computationally more advanced or mathematically more advanced methods. So I still use that a lot. Just brute force simple answers. Only whenever you again have those high cost calculations does the advantage of really going to these more sophisticated algorithms pay off. Okay, now your book moves on to looking at integration side of calculus. So what they list as the fundamental theorem of calculus, I really just look at as more of a definition. The integral from A to B of our beloved functional value f of x integrated across dx can be equivalent to the integrated function, capital F. The capital F denotes that is some unknown to this formula function that from B, the difference between point B and point A becomes the integrated value. I mean, that is the definition. That is what you follow when you're doing integration. If you've been accepted to college, I hope you've seen this before. One thing that you may not have seen before, that at least is new to me, perhaps I've forgotten it, that's mean value theorem for integrals. That is basically saying that if you have in your graphical depiction here, let's say put points A and B back to where they belong, there is one rectangular prism defined by A, a second defined by B. And it basically states that if there is an integral between these two, whatever path this function might take, that there is an equivalent rectangle between them. Let's do a different color, put some red over that. That represents the area underneath the curve from A to B. So if you think about it, A is the area that's exclusionary zone, B is the maximum possible volume that the B rectangle, that'd be the A rectangle. There has to be something that exists between the two that would represent the area underneath the curve of AB. So perhaps that's a terrible way to look at it, but it leads directly, absolutely, positively, directly to the discussion of the average value function. This is something that I've seen more students than I wish struggle with. And it's a definition that can be very useful. So average functional value of some between 2 points would be 1 over B minus A, the range of consideration, integration from A to B of the functional value dx. So you sum up the area from A to B, and then divide it by the distance from A to B. So everything between those points divided by the length scale you're using, well, that's the average value. It's basically like gathering up all the items between two locations, spreading them evenly across the space, and, well, yeah, pretty basic. Very, very elementary, but that's what we're doing here, doing an elementary review. Speaking of elementary, the next subject is vectors. So, a vector can be, I guess it could be just two-dimensional if you want. It can be one-dimensional. You could have some magnitude, say some vector 7i. I is a direction, 7 is a magnitude. Congratulations, it's more or less a one-entry vector. But in this case, you have actually the magnitude of v in the x in the I direction plus magnitude of v in the y direction times j direction plus magnitude of z in the k direction. Typical three-dimensional vector is something you'll use a lot in engineering because, well, that's the spatial dimension we live in. So that appears everywhere. In representation, in code or in Matlab, you'll oftentimes just see this annotated by Vx, Vy, Vz, either vertically or horizontally, Vx, Vy, Vz. Neither is really truthfully correct. It's just a notation topic. As a advanced bit of knowledge, it's called transpose. Same data, different orientation. You can transpose the matrix, which is what those really are. Spoiler, a matrix which is only one column or one row is just a vector. Yes. So magnitude of a three-dimensional vector, that's pretty straightforward. Actually, magnitude of any vector. There we go. We take the square root of all these subcomponents. That's it. That is the length of the vector itself. If you want to find what's called the unit vector now, that would be the vector that depicts the direction. It's really used more as like a compass, an equivalent of three-dimensional compass, because you know it's a unit length long. Well, it's pretty elementary derivation once you understand that the idea is to make a unit vector a unit length long. You would take the existence of the vector, v, in fact, I can do this the easy way. Yep. Doing it through the power of computers, I don't have to write this all again. You simply take, messed it up. That's great. Take the definition of the vector, divide it by Well, this is not going as well as I thought it would. The total length and the output becomes our unit vector. We get L in the I direction plus M in the J direction plus N in the K direction. So the unit vector is basically just the individual component divided by the total length of that vector. And that gives you the unit vector components in each the X, Y, and Z direction, or you might call that the A, J, K vector coordinate directions. And at all times, using this calculation, the length of the total combined vector will be 1. So, of course, the next topic they want me to show you is that if you write it horizontally, that's called a row vector. Yes, if you have a series of items horizontally oriented, that's a row, that's a column. Welcome to college. Okay, addition and subtraction of vectors basically happens among like components. So in this case, you would have Vx1, Vy1, Vz1, Vx2, V2y, V2z. There you go. So if you're adding these together, you would be able to just add each component to one another. V1x plus V2x goes both into the I direction. V1y plus V2y goes into the J direction. V1z plus V2z goes into the K vector direction. So summation of vectors is not a big deal. You just add the same placed components to one another. Multiplication of a vector by a scalar, yeah, it's exactly what you think. If you have a vector that is 1, 2, 3, multiplying it by 10, you go through one at a time, and this becomes 10, 20, 30. No real special rules. You're multiplying the magnitude of this original vector 1, 2, 3 by a factor of 10. So the vector becomes bigger, pointing in the same direction. Transpose, we've already covered. Multiplication of two vectors can be a bit more interesting. It's really what you often hear referred to as dot or scalar product. So let's actually get some definition here. We'll look at a vector v dot u. So just know that's the way you're multiplying two vectors together. So if you have this orientation, it essentially just comes out v I u I plus, I guess those were ones, v1 u1 plus v2 u2 plus v3 u3. Yeah, and you go up to the total length. So if you had a 5-element vector, you'd actually go to v sub 5, u sub 5, and multiply those two together. Notice that they'd have to be of the same spatial order to make this work. So not really a big problem. The interesting thing is this has an alternate definition that is equivalent. I shouldn't say alternate. An equivalent definition of saying magnitude of v, magnitude of u, times the cosine of the angles between those vectors. Now that's useful and complex at the same time, especially once you get past third order vectors. So theta is just the angle between those two, because that plane could be severely inclined in a very strange orientation, but the definition remains true nonetheless. Cross product. This is also very, very useful in vector mathematics. W equals V cross, which has a very interesting symbol, it's like a multiplication sign with a circle around it, cross the U vector. This is where right-hand rule and all these discussions come from, good in college. The definition of that becomes VYUZ minus VZUY, and that is all just in the I direction. Let's go to the next row so I don't run out of room here. VZUX minus VXUZJ. Of course, this is plus, plus. And lastly, VXUY minus VYUZ. ux k. The definition of utility here, the equivalent definition, is that magnitude of the resulting cross product equals magnitude of v u sine theta. Rather interesting, don't you think? Moving towards a discussion of matrices, we need to discuss the idea of linearly dependent or linearly independent vectors. We'll be representing equations. So basically say, if we go back to our favorite, I want to write in red now. F of x. I'll say it's something very simple. 2x plus 3y plus 7z. It's a linear function. 3 variables, x, y, and z. It's a value of 2, 3, and 7. Let's say we now have f2. Well, to be most accurate here, this is actually x, y, and z. It's three inputs. Don't tell anybody. We'll just erase these. It's inherent. f2. There's a problem if f2 equals 4x plus 6y plus 14z, because in the end that's the same equation. You just multiply it by 2. They are linearly related. You don't, in this situation, have 2 equations with 3 unknowns. The objective, of course, be finding a third that is a third equation and having 3 unknowns. In fact, that's very common. Like, you'll find some elementary mistakes happen whenever you have a third equation. So 3x plus 20y plus 1z. That one is independent. There's nothing you can multiply f1, f2, or f3 by to obtain f3. I should say just f1 or f2 to obtain f3. It's a linearly independent equation, but still, this is, like I said, it's not a system of 3 equations with 3 unknowns. It is essentially 2 equations, 3 unknowns, and therefore doesn't help you solve this system at all. This creates serious problems for matrix solutions that we're coming up to very quickly. So the last thing worth discussing is as you add together vectors, you can think of them as being spatially added. The easiest way to think about this is starting from some point 0, 0. If we had some vector that was 0x and 5y, that could be represented by 0, 5. You've moved up 5 units. And if you had a vector that was 2, 2, you move to the right 2 and up 2, which that's far too long. Let's make this better. Maybe that would be the vector 2, 2. Vector addition is basically just placing them end to end. Just like spaghetti noodles. You snap them, move them. Of course, the angle represents the points with one another. You could draw this second vector 2, 2 as being from the origin again. Again, I've assumed and perhaps didn't specify clearly enough that that large x is the origin, I'm assuming. That vector 2, 2, if it started from the origin, would be, you know, same direction, same distance, but just displaced. So all we've done is taken this vector and moved it up. That gives us the convenient result that the points from the beginning to the end is the summed vector total. 0x plus 2x, guess what? It's 2. 5y plus 2y, guess what? It's 7. Graphically, works out. That should actually go to the same point if I can just draw a straight line. But that is graphical vector addition. This works in 3 dimensions as well. This works in 4 dimensions. It works in any number of vector dimensions that if you add 2 vectors and you can place them end to end graphically, and then the point between the original placement and the final placement is the resulting vector solution. It doesn't work with just 2 vectors. You could have a third vector hinging off, you know, this way, and then the fourth one can go back here, and then the summation of all of those, boop, done, graphically at least. So that is the end of vectors and the calculus review, and we really just covered high school all over again there in a nutshell. Next we'll move on to discussions of matrices, matrix addition, transposition, but that's another time for another video.